The next thing that we need to discuss is the idea of a differential. And you know how when we write this dy dx, in the past I told you I really like this dy dx notation here because it kind of looks like a slope. Dy is like a very small change in y. So delta y is like a big change in y, dy is like a small change in y traditionally. And then dx is a small change in x. So this kind of looks slopey. And what we're going to do is we're going to take this, we're going to split this in half. We're going to think of the derivative as a quotient of two differentials. We're going to multiply both sides by dx. So that's kind of what we get over here. Okay. And what is the purpose of a differential? Well, we can look at this picture to capture the purpose. Okay. What we want to do is we want to say, you know what? I'm going to change the x by a little bit. And what I want to measure is I want to measure if I change the x by a little bit, how much does the y change? Now I can find the true change just by subtracting. So the length of this red line here, this is the true change. We call delta y the true change. But I can approximate this red length here with this blue length. And this blue length is the differential dy. And I can calculate this blue length just by calculating the differential like this. So just to emphasize, we're changing x by a certain amount, and that's going to be our independent variable. I want to see when I change x by that much, how much does the y change? That's this red length over here. I'm going to approximate it with dy, which is the blue length. And as long as this delta x is not too big, this dy will be a good approximation. So that's what this highlighted part here is saying. Okay. So let's take a look at an example over here. Let's take a look at example 5. When I look at example 5, what I'm trying to do is I'm trying to calculate this differential. So I know that the differential dy is just going to be the derivative multiplied by dx. So that means dy is going to be equal to 2x plus 2, put that in parentheses, dx. That's it. Differential is easy to calculate. Now they give me specific numbers, and they want me to calculate both the delta y and the dy. And that's at x equal to 3, and they give me this small change. So I'm going to calculate the dy part first. So we're going to put dy, we're going to put a vertical bar, that means evaluate it at x equal to 3. And then what I'm going to do then is I'm going to plug in a 3 for x. And I'm going to replace the dx with the 0.1. Okay. So when I do that, I'm going to get 8 times 0.1, and that's equal to 0.8. So that's what my dy is. That's the approximation. Now what I want to do is I want to actually find what, that's a good approximation, I think, but what's the real change in the y values? So to find the real change in the y values, you need to subtract the 2 y values. Okay. In other words, we're going to need to plug in a 3.1. So we'll have 3.1 squared minus 2 times 3.1 minus 3 squared oops, that's a plus, my bad. Plus 2 times 3. So maybe I'll include one extra line, actually. I'm slightly worried you don't follow what I'm saying. I'm saying we're basically taking f of 3.1 minus f of 3, because plugging in the y values are the function outputs. And this is what we get. And then when you stick this into your calculator, you're going to get 0.81. And that's your delta y. Okay. So when we compare the two values, I hope you can see that the true change, this is the true change. And this is the estimated change. So you can see these two numbers are pretty close. All right. Cool. Any questions for me so far? Oh, I'm sorry, Desmond had a question. Let me go back. So he says, so you got 3.1 by adding x and dx. That is correct, sir. So in our picture over here, this is 3. I'm going to add the 0.1. That's how I get this 3.1. So I'm going from 3 to 3.1, and I want to see what the change in the y values are. Okay. All right.